All right, thank you very much. Again, my name is Hong-Shig Shim. Can you hear me? All right, from Reaction Engineering International, I'd like to talk about reduced chemical mechanism for chemical looping combustion system. It's a DOE project, so there's a disclaimer. I'd like to give you just Oh, yeah. All right, I'd like to give you just a brief introduction to REI. So we are a consulting firm known for independent analysis and evaluations involving a range of industrial reacting flow applications. And our technical focus is on the multi-phase chemical reacting flows, combustion, gasification, fuel conversion, and pollutant emissions in the various reacting systems. I have been serving the industry since 1990. We have affiliates in Asia and Europe, have established capabilities including advanced modeling process evaluations and testing. Testing is we perform the kind of bench scale, pilot scale in collaboration with universities and other research facilities. All right, chemical looping combustion. This has been studied for a while as one of the ways to separate and remove CO2 from fossil fuel combustion system. It's made of two reactors, air reactor and the fuel reactor. Use the metal oxide to transport the oxygen from air reactor to the fuel reactor to react with the fuel. And the metal oxide itself can react with the fuel, but if your fuel is a coal, this is a solid-to-solid reaction, so it can be very slow. So people try to gasify coal first to using coal gasification and have metal oxide react with gas. But coal gasification stage is also slow as well. So another way to do this is using a metal oxide that releases oxygen in the fuel reactor spontaneously in the right conditions, of course, and then have that oxygen react with coal. So this becomes like a typical fluidized bed combustion system. So that's called CLOE, chemical looping with oxygen coupling combustion. We're interested in metal oxide. We want to use this cupric oxide system. REI is collaborating with University of Utah and CPFD to improve chemistry chemistry description for CFD simulation under this DOE project. So coal is, as you know, is a very heterogeneous material, and the coal reaction can include various homogeneous, heterogeneous reactions, and it's including devolatilization, and those volatile species can further react homogeneously and heterogeneously. And the char oxidation is also there, and char gasification. And also, because we have another entity here, oxygen carrier, that can react with, so for example, sulfur-containing species can interact with the oxygen carrier that by forming a sulfide or sulfate, it can deactivate the efficiency of the oxygen carrier. And also, agglomeration can happen and change the circulation pattern in the system. Also, SO2 release is a sulfur. So SO2 release is also an emission concern. It has a nitrogen, so NOx and TOR is obviously a concern as well. But practical combustion system chemistry includes dozens to hundreds of species, hundreds to thousands of reactions, and the detailed chemistry is not really feasible for CFD simulations for over practical devices. So present simplified schemes may not work under sufficient broad range of conditions. That's why we propose to use a reduced chemical kinetic mechanism. We use a CARM, computer-aided reduction method. Is software developed by Professor J.Y. Chan and students at the UC Berkeley. And the main objective is to reduce the number of species you want to deal with, and while maintaining behavior of original system. So for the development, you have to define your parametric space of interest as a function of temperature, pressure, stoichiometry ratio. You want to define your species and the reactions. And based on that, you can establish detailed mechanism, run some simple reactor codes, and fed into CARM, and use those information to develop a skeleton mechanism, run this code again, reduce and optimize, and come up with a reduced mechanism, and can be used in the CFD codes. Key in the reduction optimization is we are assuming some species are in the steady state. So that means the net rate of production is negligibly small, so that we don't have to worry about those. So by doing that, you minimize errors against the detailed chemistry, and our objective function could be temperature, species concentration, ignition delay, as you like. And we can also specify major species can never be in the steady state, so that you can track those major species. Or minor species, you don't want to track them. And then you can specify that in the development. And produce subroutine that serves for steady state species and the reaction rates. Has been applied to various systems: NOx control, SOx control, hydrocarbon combustion, hazardous chemical incineration, such as chemical weapon destructions. So I just want to give you some examples using reduced chemical mechanism in NOx control for coal-fired boilers. Just a little bit of chemistry. Coal has nitrogen that can be devolatilized in the reacting system, can form a volatile nitrogen or tri-nitrogen, and volatile nitrogen can form HECN. If it reacts with oxygen, it forms an NO, and if it reacts with NO, it forms N2. And tri-nitrogen can be oxidized to NO, and then or react with NO to form N2. This is called the fuel NOx route. Another route is the thermal NOx. Is at high temperature, nitrogen in there can react with oxygen to form NO. Another mechanism is a prompt NO. Hydrocarbons react with the nitrogen and form the precursors, such as HCN, to form NO. There's another the reburning mechanism. Fuel can form CO, unburned, and then the hydrocarbons can react with NO to form HCN that can follow this route again. And there's another chemical use for control methodology. Sometimes you use a reagent. Nitrogen-containing compound can react with the NO to form N2. But of course, if you put that chemical reagent in the wrong location, it can be oxidized, and you are forming NO instead of converting that to N2. So that's very important. So another thing is char can also reduce NO. So this you have to have a good understanding of chemistry so that you can come up with some control strategies. So we developed a reduced mechanism and applied to coal boilers. I just want to give you two examples. One is air staging. I think this is a furnace and a low furnace. And the basic idea is take out some portion of the air from this lower furnace and inject in the downstream so that burnout zone is there. So in the fuel rich zone, you want to promote that nitrogen to N2 conversion instead of NO formation. And the remaining fuel can be burned in this downstream. Another one is a little bit complex. It's called advanced layer technology approach. We have developed this technology with the DOE. In addition to OFA system, where staging, you add some chemical reagent injection in the various locations. RRI is called this rich reagent injection, so that you inject, it's a similar compound as used in the SNCR, nitrogen-containing compounds into a fuel-rich zone. Basic idea is that this is a high-temperature zone, and then can use fast chemistry. Of course, if your RRI reagent meets oxygen, you're screwed. So you're going to form more NO instead of a conversion to N2. SNCR is the same way. So to optimize this control strategy, again, you have to, first of all, you have the good fluid dynamics, and also you have to have a good understanding of chemistry and the right tool to evaluate that. So this is air staging before and after, some modeling result before and then after and there's some testing results. So first of all, it's a good agreement, and we could achieve over 25% reduction. Advanced layer technology, this is plant data, is firing 445 megawatt gross. This is, that the loading is maintained at the same level during the testing. Here's RRI flow and SNCR flow rate at different time. Here's NOx, initially is OFA 0.23, and then with RRI 0.16. With ARTA, we could achieve 0.12. This is overall 90% reduction from the uncontrolled NOx emissions. So this provides some good tool to optimize your control strategy. So let's go back to the CLUE system, chemical looping combustion. We, as a part of the DOE project, we want to improve our chemistry again. We used to initially start with the previous setup, which is developed by University of Utah, in which they assume that use a relatively simple approach. Coal is devolatilized into only 4 species: methane, hydrogen, CO, and CO2. For gas phase reaction occurs, and metal oxide reaction, and then char oxidation. Char is also assumed to be made of just carbon instead of, again, it can have other material. So more detailed approach is needed. So what we did is, in the same, starting point is the same. We assume that the coal is made of 4 entities: moisture, volatile, ash, and char. But volatile is predefined, it's pre-calculated, this yield, using the chemical percolation devolatilization model under relevant thermal conditions. And the volatile is assumed to form 7 species made of CHNOS, and the char is made of CHNOS again. Of course, if we don't know the exact composition of these volatiles, we can assume that volatile and char have the same CHNOS as in the coal. You can get that from the such as ultimate analysis. All right, based on that, we can define the coal devolatilizing in this way and then provide energy balance. And char oxidation, we changed it a little bit in the char oxidation as well. Now you have a CHNOS, and also we use a CO2 ratio you can find from the literature value. Because as you increase the temperature, there are more CO formation than the CO2 formation. So we want to kind of capture that behavior. So we use the CO2 ratio as a degree of reaction. And then we can provide energy balance. And some other reactions, gasification. CO oxidation also has been revised that there's an impact of water. So even though it can be canceled out, but there's impact of water, so we want to capture that behavior as well. So we added that. So now it's this kind of intermediate setup. We have a more detailed approach for coal devolatilization, speciation. CO oxidation has been changed, char oxidation has been changed, and added some additional reactions. But we still don't have a sulfur and nitrogen chemistry. For that, we want to use a reduced mechanism. So all the gas phase reactions in this setup will be replaced by a reduced mechanism. So that's our final setup. And going back to the reduced mechanism development, we have to have a detailed chemistry first. So we used the REI97 mechanism, which combines coal natural gas combustion and NOX chemistry based on this reference. And there has a sulfur chemistry as well, and the nitrogen and sulfur interactions. So we ended up with 101 species and 557 elementary reactions for detailed chemistry. With that, we came up with 25 species, and then show some comparison between the detailed and reduced mechanism. Our parametric space for this is a stoichiometric ratio 0.5 to 1.5, temperatures ranged here, resonance time. Here's some hydrogens, CO, CH4, CO2, showing that concentration calculated, concentration calculated by reduced mechanism and a detailed mechanism is called the parity line. So if they lie along the diagonal line, is good agreement. They show the good agreement. A nitrogen-containing compound, ammonia, HCN, NO, and N2 are all a little bit scattered, but still they're showing the good agreement. Sulfur-containing species as well, and with the oxygen. So we have this framework of chemistry that can be applied to the next step. So now we can look at for example, impacts of coal. Coal, different coal has a different composition, so we can certainly evaluate that. For that, going back to chemical looping combustion system, University of Utah is developing so-called chemical looping combustion process development unit. So PDU is basically 2 interconnected circulating fluidized bed. Here's a fuel reactor, air reactor, but we're going to just look at the fuel reactor for this purpose. So there's some initial metal oxide particles. Here's the riser section, comes there in the Cyclone and downcomer. And there's deep leg, and steam are injected from the bottom, and coal is injected with the with the steam. Core properties, we look at the Illinois number 6. This is a high volatile bituminous core, and PRB is a subbituminous core. Subbituminous core is a little bit younger core than the bituminous core. Nitrogen is different, 1.2, 0.65. Oxygen is also a little bit higher in the PRB core. And the sulfur, 3%, 0.2%. That's one of the reasons people want to use actually PRB core for their system. And H2O is moisture level is a little bit higher, and the heating value is a little lower. This is a result of the CPD calculation. Illinois number 6 shows about 54% volatile yields under these thermal conditions, and PRB core shows about 61%. So use that to balance mass, and here's some results. Just showing the only core particles, volatile mass fraction and carbon mass fraction. As you inject your core particles into a fuel reactor, your volatile fraction will start high and then decrease as you release volatiles. And the carbon mass fraction will initially increase because you're releasing the moisture and volatiles, and then decrease as the reaction goes along. So major, it's hard to compare by looking at just the movies, but because of the amount of moisture and volatiles in the PRB, it takes a little bit more time to devolatilize. And some gas composition and model exit. In the fuel reactor, you expect to have a lot of H2O, of course, and then followed by CO2. That's one of the reasons you want to increase the percentage of CO2 in the system so that you can remove. H2O is here similar, CO2 is similar, but its PRB core ended up with a little bit higher oxygen. And it's a nitrogen-containing species, and the N2 is higher in the Illinois number 6. NO is slightly lower, and N2O and NO2 are similar. But biggest difference would be SO2. Illinois number 6 shows a relatively high value than the PRB. Of course, you start with a very high sulfur fuel. So we look at the fuel PDU simulation using just the Illinois number 6 core. This is a kind of a similar setup, fuel reactor part, and the air reactor part is just that you inject air through the system, and the metal oxide is circulated the whole loops. And we used 3 different species with the different compositions, same metal oxide, but high cupric oxide in this here in the red color, and the lower, a little bit relatively lower, cupric oxide composition there. With that, this shows a particle flow by species, colored by species number 1, 2, 3 for metal oxide, just to show that after a while is fully mixed. So at about 160 seconds, you can see it's well mixed. And these red colors pretty much reside in the fuel reactor. These are core particles. That's what you want to do when you achieve that. Okay, the core reactions and some core particles go into a reactor, but of course, this under given conditions. So this is kind of things that you can optimize later. And some CO reactions are also release of a CO, and initially it's pretty much from the volatiles, and the CO formation, and the related, this part would be from the char conversion. NO, N2O, NO2, basically we can predict those nitrogen-containing species. And here's the reactor outlet concentration. Fuel reactor outlet, again, H2O is the major, and CO2 followed by CO2, O2, and N2. And the CO2 is, on the drive axis is about the 64%, but certainly you want to improve that to higher CO2 concentration at the outlet. And SO2 is about close to 2,000 ppm, NO about 166, NO2 and N2 is a small, less than 5 ppm. So with that conclusions, we developed a 25 species reduced chemical kinetic mechanism, compares well with the detailed chemistry. And the reduced mechanism show a promise when implemented to a Barracuda VR. this again provide the framework so that you can further utilize this framework to evaluate or optimize your reacting flow system, and also come up with some control strategy. And the result will be compared with any available measurement. Actually, University of Utah is working hard to get the data, so then we can kind of compare and validate the model, and if there's a need, that further model requirements will be made. That DOE is funded by DOE, thanks to Zach and CPFD for providing modified Barracuda VR code for this study, and then giving me an opportunity to talk about this study here. All right, thank you very much.
Thank you, Hong. What questions do we have for Hong? Dirk, there's going to be, wait for the box, it's coming. And then Avinash, you're next. Oh, we're doing the other order. Avinash is first, then Dirk. We're going to follow the mic.
Nice presentation. My question is regarding the ash and the coal. In terms of the CPFD boundary conditions, how are you rejecting the ash from the coal once it's reacted?
You start with as a coal and then define the coal with those 5 species, CHNS, volatile species, ash, and then moisture.
No. So at some point, the ash has to leave your closed loop system, or it's going to build up as you're feeding coal. So is that handled through a boundary condition, or?
No, as a boundary condition, just total particles. So yeah, it has to go through that reactor cyclone outlet.
In fact, let me just ask a follow-up question on that. In the actual PDU, is there an ash drain or something over time if they're running it longer, or how does the real system work?
That's a very good question, actually. It has not been running yet. So.
Okay. To be determined, and you have some insights behind your question, I'm sure.
Maybe you said it and I missed it. With the reduced mechanism, you said how many species you have, but I don't recall.
25.
Right, but I don't recall you saying how many reactions you have.
19 steps. I didn't say that.
19 steps.
Yeah. 19
reactions, 25 species. And how many of them would you consider stiff and reversible?
I mean, for this for this chemistry development, those 25 species, one of the difficult thing is H2S, a couple of species, because that's a low temperature and the lean conditions is hard to predict the detailed chemistry behavior. But I say maybe a couple, and then other was.
And how many of them are of the 19 reactions are competitive reactions involving more than one species? Sharing species between reactions, I mean.
That I cannot. I don't know actually. That the reaction steps are based on the reaction rate.
Yeah.
So we don't really provide that information in the world step by step.
Okay. Is the mechanisms referenced publicly somewhere that I can I review?
Oh, yeah. I guess we can do that. Actually, we have that should be in the DOE report because it's part of the DOE project.
Okay.
So it should be there.
Okay. All right. I'm just asking these questions because I've got my mind thinking about how I can accelerate the chemistry. So.
Sure. Yeah.
Great, and that's a conversation to keep going. We have a question over here from Adlan. Wait for the mic, if you will.
Perhaps I missed something, but I don't really understand why we need a modified version of Barracuda to implement the reduced mechanism.
Oh, CARM actually produced a routine that actually Fortran routine, and then the Barracuda needs to expose source term for the reaction rates. Probably Jim can answer better, but that exposure is not available in the commercial version. So he has, CPFD need to modify the code so that it exposed those source terms.
Yeah, I just comment that, yes, it's a Fortran routine that's calculating reaction rates or kind of net rates for each individual species. And so then we integrated that into the chemistry solver in Barracuda, and we're running these calculations in addition to the volume average chemistry and the discrete chemistry. So they were able to, in the case where there was the solid chemistry, that was able to work together with the chemistry being calculated from the routine.
And this is an example of where we're, again, exploring what could be possible in the future, working with the knowledgeable partners and informing our development process going forward. So let's thank our speaker one more time.